Oh, you are going to be here. Sorry? Oh, Thursday. Yeah, are you here? No, I have not take race. Yeah, I need Scrubber. You can do Scrubber?
No, I can't. Because I had to set my account.
No, I see you taking it. Michelle.
There are no pens for either, or I've got an extra pen here. Backpack. Should be okay.
Fine, how are you? I'm moving back to my room until Albert reports me for dinner.
Guys, we're still looking for Scrubber. Anyone? Yeah. Guys, anyone scribing? Not drinking beer? What you did? Thank you very much. So good afternoon, Routing Working Group. Welcome to Yokohama. Happy to see you. Today is our first meeting, second meeting on Thursday, same time. Not well. Anything you disclosed during this session, during IETF plenaries, is in according to rules described in RC 5537-3979. So we are going to poll you on IPR when we adopt the draft as a working group document. We are going to poll you again when we go to working group last call. Please note, if not all authors on the list and contributors have responded with IPR statements, document will not proceed any further. Thank you, AC Linden, for taking notes. Thank you for Trevor Person. Please sign the blue sheets. So the agenda for today is us, obviously, Jeff and Chris. Gunther is going to talk about flow spec or indirect path, that's renamed. We are going to talk about microloop avoidance using segment routing. We are going to talk about BGP peak implementation and CISC routers, I assume. We are going to talk about keychain and RIB extensions, young models. So you've seen charters updated. Besides core items of routing working group, we're also taking on items which don't fall into charter of any other routing working group. We act as dispatch, so we give you a home to present and then dispatch it into more suitable working group. So in terms of milestones, remote LFA has become RFC 7490. Multicast only faster out after 6 years. We've gotten RFC finally. What we are looking for November is to get LFA manageability. It's been in editor queue for quite some time. We are working on alignment with some other drafts. Hopefully it will progress soon. We've got remote LFA node protection in routing review. We've got really good comments. They've been really good discussion with Stewart and author, so they're getting close to resolve all the points. MRT, significant updates have been published, so we are working to progress. Yes. And by next ATF, we would like to submit MIB work to IETF. So, status of documents to RFC since last ATF. We've request publication for operational management of LFAs. 4 new working group documents, 2 of them YANT models. The destination source routing relevant to HomeNet in microloop prevention. BGP in large scale data centers ready to be submitted to ASG, going to be done immediately after IETF. T4. So we are working on MRT stuff, which is going to be ready by next ATF, as well as MIP for LFA. And first presentation is. Yeah. Gunther? You could use the point. Yeah. No, you're all good.
Yeah, again. And I think this time I might even have animations. So.
And it's a PowerPoint.
And PowerPoint, yeah. There is no ending. So just how many of you actually were in IDR like 5 minutes ago? It's an interesting poll. You know, it's only 30%. Okay, so what I'm going to be speaking about, so the problem I'm trying to solve is that, you know, if a packet enters a network, then, you know, on a router, then what the router does most of the time, it sort of sends traffic to the shortest path to the destination. Now, in some cases, you do not really want that to happen, because the shortest path towards destination might not be the best path, because you want to deliver like a particular service upon the packet. So you actually send it into a tunnel or on a particular interface for DDoS scrubbing, whatever. Now, you can do that right now. And in the main way of doing that, most of the time is by using policy-based routing. Now, PBR by itself has been orchestrated and using like full spec rules. And that is what this thing is allowing you to do. It sort of sends you an identifier for a redirect service. So the draft, what I'm which I'm presenting here is like, playing in the IDR working group. But some of the implications, might actually hit here as a bigger, routing aspect, and some of the context might actually, be interesting from a routing perspective. So the first thing is that pod ID created an incredible amount of confusion with people in their brains. So if you read the draft, just do the mental swap. Pod ID is actually indirection ID. It is just 32 bits or 128 bits. It's opaque data. And it will identify something, and we will discuss later on what exactly it identifies and how it can be used. So again, what the motivation for this is to allow for a controller to tell routers what to do with traffic and where to send the traffic, which tunnel to send the traffic. What we are not trying to do is to signal any tunnel encapsulations or set up tunnels or these kind of things. So when you look into PBR, it actually has like two main tasks if you configure the PBR rule. The first thing what you do is you configure match criteria. So you actually identify the traffic that interests you. The second thing what you do is you identify what you're going to do with the traffic. And those could be two things. The first thing is you condition the traffic, so you police it, you shape it, you recolor it, and all those things. And the other thing what you do in the policy-based route is you send traffic to an interface, to a tunnel, and so onwards. So if you look into flow spec itself, then the matching is very well covered, traffic conditioning is very well covered, but the traffic steering itself is only covered to a degree. You only do traffic steering into the VRF. You don't really go beyond that. There have been some extensions. There have been some extensions to it, and towards IP address. So in essence, and that is where indirection ID comes into play. It's actually a mechanism which will allow a flow spec controller to signal towards receivers on where to send the traffic which matches, which you think should be redirected. So this would be a wonderful controller, and we have our matching criteria, what you see here. So on this picture, we actually have like 4 flow spec rules, rule 1, 2, 3, and 4. Each of them actually has their own match criteria, and it already has, based upon RFC 5575, some conditioning information like policing, recoloring, and so onwards. So what we're going to do now is we're going to add a new community, which would be the indirection ID. Again, 32 bits or 128 bits, opaque data. And it's actually an abstract reference to an indirection. So the controller sends this thing to all of his BGP peers. So now these peers actually have this information. So now, and they all receive the same, for the particular flow, they will receive the same indirection ID. So for flow 1, router 1 will get indirection ID 1. On router 1, for rule number 2, it gets like indirection ID 2. On router 2, for first flow set, it will get indirection ID 1. Router 3 will get for the first flow set also indirection ID 1. So how do these routers actually use it? So, and that is where, the main reason where, why I wanted to introduce this work also in this particular working group is because we create like a new table here, which is the indirection table. So on router 1, for example, we actually create a table which is indexed based upon these indirection IDs. And next to that, we have information like indirection ID means, could be like a segment routing tunnel, recurs to that one. Indirection ID 2 could be like an eVPN, ESI, redirect traffic. The third one could be manually configured. The fourth one is just an IP routing table lookup. So these are things, you actually place in this indirection table. Now, how does the table get populated? Is through whole sets of different kind of means. So the table itself is decoupled from any flow spec signaling at all. Flow spec just signals the indirection ID. And the table itself is like independently populated. So this means you could use it, by existing technology. Could be a traditional routing, could be netconfig, could be XML over XMPP, manual config, all these kind of things. But it gets populated. So this table can be different per router. So that means on router 1, for example, my indirection ID 1 means it's a segment router tunnel going from router 1 towards router 5 towards router 8. On router 2, however, the indirection ID 1 here says like, okay, it's also a segment routing tunnel, but it's going from router 2 towards router 7 towards router 8. On the third router here, router number 3, the bottom one, indirection ID 1 actually says like, okay, I need to redirect traffic here towards an RSVP TE tunnel, going to router 9 towards router 8. So indirection ID is the same. The tunnel information itself is different per device. So what does this mean? So how would it work? So the first thing is on the router, we have this indirection table. So router 2 has a table, what you see there. Router 3 has a table, what you see there. These tables are different. The indexes are the same. The indirection is the same, but the way it is, the information for which the indirection stands for is actually different per device. So imagine on router 2, we have a packet entering. So we identify the packet, we look into the header, and we say like, okay, this matches, the stuff from flow spec rule number 1. We do a match. We identify, the packet needs to be redirected into this segment routing tunnel, going to router 7 and then to router 8, and we ship off the packet. On router 3, however, assume we also get the packet, and it also matches flow spec rule number 1. It says like, oh yeah, it's in direction 1 here, but on router 3, it actually stands for, okay, this tunnel, is actually now pointing towards an RSVP tunnel from router 9 towards router 8. And think about these tunnels, are already set up in your environment. They are up and running. So that is what we have here. So with one indirection identifier, we identify like different tunnels going through the network itself. This allows you that on each of these, routers consuming the flow spec rule, that the next hop could be either IP address, could be, an MPLS tunnel, could be basically whatever. So each router has, by itself, figures out this thing by means of like local recursion. So, and that is the main thing what I wanted to present here, and the key, So the way it is actually constructed, so it's a community, 32 bits, 128 bits value, one of the two. We have a C bit, a copy bit in there if you only want to redirect traffic, or if you want to send a copy of the traffic to the redirection path. And you have a thing what is called like TID, tunnel ID, which means, in this case, only reserved like 2 bits, meaning you have like 4 different tunnel IDs in case you want to use like, nested tunnels, between each other, for the use case actually you might have in mind. But coming back to this, just going back, because that is more the focus of why I'm presenting this here. Yes?
1 minute.
1 minute. That's my last slide. So creating this tunnel ID table, we have like different means of doing that. So I think initially it's probably going to be like manual configuration to do this, because you only have like a limited amount of tunnels on your boxes. You pre-configure them. In the future, the whole thing will probably be orchestrated. Now, some of the things what I put on here is like, on the other screen, is like how it could be populated, could be based upon extensions to routing protocols. And that is, where I'm gonna, leave the room, to the mics open here, if there would be.
Robin from Huawei, I have concern related. Oh, okay. I think here you mentioned that the indirection ID will you based on the configuration, or how you even allocate the indirection ID?
The indirection ID is just a 32-bit or 128-bit number.
Sorry, what number?
It's a 32-bit number or 128-bit number. How you allocate it is based upon how you're going to be using this. So you could be doing it manually, but if your use case requires you to have like 1 million of those, it's not going to make you very happy doing it manually.
Okay, and also next question: what's the use case? Use controller use case or some of the traditional flow spec case? Okay.
So, Keyur Patel, Cisco, speaking as a co-author. You want to think of heterogeneous networks with multiple different forwarding planes, and or you want to think of a network with a multiple tunnel encapsulation. And just as you have an underlay and an overlay, you want to think of this as sitting between an underlay and an overlay, doing a tunnel abstraction layer, and so as to form a tunnel table, right? So it hides tunnel encapsulation of different types completely through the indirection ID.
Yeah, Kyo, but my question is that the tunnel, the encapsulation can be hidden, but the problem is the indirection ID must be seen by the server or the controller. So I mean, so how you implement this one configuration? And also I propose the use case, the meaning is if this is the controller or the traditional the flow spec server. So how the server or the for the server or the controller, how to get to know the indirection ID? That's my concern. So I mean,
yeah. So the setup of the tunnel itself is actually completely, beyond the scope of this piece of work. So the way, the tunnel, the indirection ID is the indirection ID. If you set up a tunnel, you assign it that indirection ID. You can do it manually, you can do it orchestrated. So it's completely open. Don't see where you see the problem.
Okay, so I think that's the important issue for the user case, and also how to deploy the feature in the controller or the configure or the flow spec server, because I think this is the important one. So my last comments is that I propose the segment routing path programming in the Spring working group. I think the segment ID has also the meaning to represent the next hop, represent
Robin,
the tunnel.
Please take it to the list.
Oh yeah,
Become
okay.
personal discussion.
Yeah, I think it can be converged.
Aaliyah Atlas, no hats. So as I mentioned in email, the indirection ID, I think, is exactly the next hop ID, which is client assigned in the I2RS RIB Yang model. I think it's exactly what you want. It does absolutely this, and you should really take a look at it. Then that Yang model can obviously create the next hops using RESTconf, NextConf, whatever modification of I2RS that we have. It's ephemeral state, which I think is what you're looking for here. And it lets you refer to dynamically created tunnels and so on, which I think will solve that piece of the problem.
maybe one comment, Wim Hendrik from Octalucent. It's not only it can represent not only the next hop. Next hop is one of the use cases, but it can be more than next hop.
Okay, so
Yeah, yeah.
And Kevir Patel, Cisco, one more time. Just to clarify, it may not be ephemeral also. It depends on the policy.
So no, not surprisingly, we are presenting in PC working group draft, which uses exactly the same terminology. I would call it direction ID, really. It's a policy ID. You magic the policy ID, you do something with it. So we also talk to Sue from I2RS. We'll start working across working groups on creating abstracted policy models, so it could be distributed through NetConf or any other way. You're in charge. This thing has a laser pointer or has everything? Just want to point. It doesn't. Ah, which one?
My name is Ahmed Bashandi. I'll be presenting the BGP pick. Next slide, please. Where I can do it from it. Oh, okay, good. So I'll talk about the problem, the solution, and one thing that, let's see this. Okay. One thing that I got comment about and I added it in the next version was how to handle hardware limited capability. And I'll talk the use of this solution and its applicability in recovering from various failure scenarios. Problem. Whoa, okay. So I'm not sure if I should say this or not, but BGP is kind of slow because it's serial in nature. Things have to be understood and then sent to the other one. The objective of this architecture is to be able to recover from various failure scenarios as well as from various up scenarios in a time complexity that does not depend on the number of BGP prefixes. And to extend this is not specific to BGP prefixes, it's also applicable to pseudo wires and to anything that basically has a level of indirection. I have a few terms. Basically, a leaf is a prefix. You can think of a prefix. A path, everybody knows what a path is, either a next hop or a next hop plus an interface. A path list is an array where one of them is picked based on some sort of load balancing. The out label array is the label that you push. So label number 1 will be pushed if you pick path number 1. Label number 2 will be pushed if you pick path number 2, and so on. And the last one is the adjacency. It's basically the layer 2 encapsulation. Solution. So BGP pick is, to be honest, is not a BGP feature. It is actually a FIF feature. And as I just mentioned, it works for pseudo wires. It need not have BGP at all. The idea is to construct the forwarding chain in a hierarchical and shared, and do the hierarchy and sharing as much as we can, so that we avoid having to change too many things for one small thing. Once one small thing changes. The nice thing about it is that it is internal behavior, it's completely transparent, it is incrementally deployable. You don't have to have it on all your routers. This is the example that I will use. I have basically 2 egress PEs advertising 2 prefixes, and to reach each of the egress PEs, I have 2 internal or 2 IGP paths. This is very a simple example. If I want to construct the forwarding chain, here are the 2 destinations. This is destination number 1, and this is destination number 2. Here are the 2 egress PEs. Now, if you look at egress PE resolves via an IGP prefix, internally learned via SIS or OSPF. And if I'm running segment routing or LDP, it will also have labels on top of it. Path number 2 resolves via another IGP prefix, and it has different paths. Now, if you look at this structure, you can see that because these 2 IGP destinations share the same set of next hop, I construct the same path list. Same is true for these 2 separate destinations. And that this could be 100,000 and this could be 2,000. Just 2. And the important thing is that the label here is different from the label here. So even though they share the same set of paths, they have different labels. Because of course, the local, if I'm using just per VPN or even per next hop, the label advertised by this guy certainly may be different from the label advertised by this guy. This is just a forwarding chain. If you see, I did a lot of sharing and a hierarchical, and we'll see how we can benefit from this. One note that I got when I published the first version is how do I handle the case where I have limited number of recursion levels, number of hierarchy. Let's say my platform supports only 2 levels and I have 3 levels. So I came up with an example in the version that I did it in a very quick manner, and it wasn't really because it was tight, like I did it a couple of hours before the deadline. So I'm going to use a different example here. This example looks scary, but it is not actually. It's a simple enter AS option C. The only difference is that in case of option C, to avoid having two recursion levels here, these ASBRs will advertise the core routers of this domain into the IGP here. What I'm proposing to add an additional level of indirection is that this ASBR would advertise the core routers here via BGP to this guy. So that would just add another level of indirection. And again, I have the same destinations, the same ingress PE, except here I chose 3 ingress PEs. I could have done it with 2, but basically it's just something that I did in a bit of a hurry. If you look at the structure here, again, I have 3 levels of indirection. This is the destination. These are the PEs, and these are the ASBRs. Again, I'm trying to share as much as I can. If you look here, I am sharing. These ASBRs are shared by all the core routers here. Each one of them has a separate label. These PEs could be shared. Each of these path lists could be shared by several thousand, even several 100,000. This is basically a forwarding chain if I have 3 levels of hierarchy. 1 level here, a 2nd level here, and a 3rd level here. Now, suppose my platform supports only 2. My ASIC supports only 2 levels. In my packet budget, I can only do 2 levels of lookups. So how do I do this? We need to do some sort of flattening. So I took this guy and I flattened it into these 2 path lists. So I ended up with 2 flattened path lists. If you see, these 2 blue were collapsed into 1. These 2 green were collapsed into 1. How do you flatten it? To be honest, it's a lot of details, and I don't think that I'll be able to cover it in this presentation. But the point here is that as I will show later, I did lose a little bit of my sharing. Okay, now how do I use all of this? Now the objective of all of this, as I said, is to recover as quickly as possible in a time complexity that does not depend on the number of BGP prefixes. So I'll cover a certain simple core scenario. I had a path and something broke here, so I need to change that internal path. I did not lose reachability to the egress PE, so I still have 2 egress PEs. How do I recover? What happens here? So let's look at the forwarding chain. This is the original forwarding chain. I was going via interface number 1. The link broke. So what I did is that IGP recalculated the path towards the same PE and found next hop number 2. What happened here? I only had to change this part. I did not have to change anything up here. This could be, again, 100,000 leaves. But what happened is that even though 100,000 leaves are taking now a different path, 100,000 traffic flows are taking a different path, yet I only changed one small piece, which is this path list. Let's look at the second scenario. Let's say I have a primary backup. So let's say this is my primary egress PE and I had this as a backup PE. Let's say something happened that I no longer can reach this guy, so I need to use the backup PE. Now, all traffic destined to this destination needs to go via a new PE. Originally, it was going out via PE1. Now it is going out via PE2. Again, I could have 100,000 of these. How do I fix this in a time complexity that does not depend on the number of these destinations? Let's see what's happening here. This is my forwarding chain. This is my backup PE. This is my primary PE. Now remember, each of these VPN leaves, and again I'm using VPN leaves because they are labeled, has a different outgoing label, which means this guy here advertised an outgoing label that is different from this guy, and I could have here 100,000 of this. So how do I do this? Originally, we used to follow this path, which means we match an IP packet, I push this VPN label, then I push this LDP label and goes out here. Now, suppose this guy dies. What do? All we have to do is to correct this path list. The reason is that all leaves that were looking at this path list are sharing the same set of path lists. So all I need to do is to fix one path list only, or maybe few, 10, 15, 20, 30, but definitely not 100,000, definitely not 200,000. So that's one second failure scenario, which is an egress node failure. The third part, which is PECE link protection. So on PE2, I pre-programmed a backup path saying that if this link failed, please reroute the packet this way. So when this link failed, now remember when this link fails, it takes a little bit of a while until PE1 knows that the link has failed, especially if I'm using next hop self, it's going to take a little bit more than a small time. I need this guy, when it receives the traffic and detects that this link has failed, that it would reroute the traffic via the second PE, and PE2 would definitely send the packet out. This failure scenario, because it relies on local failure detection, we can do it in 50 millisecond or sub 50 millisecond time frame. Let's see how we construct the forwarding chain again on this node. So again, I have a very similar routing chain, again, the same sharing. The only difference is that the backup label is unlabeled. When this node sends the packet out, it sends the packet as unlabeled. But if it pushes it back to PE2, it needs to push the VPN label that PE3 advertised for this prefix. So forwarding chain is very similar, except that I have a different label structure. Again, this node fails. This egress PE no longer reachable. All we have to do is to reroute the traffic via the second PE. Again, what I did is I changed a single path list. I did not have to change a possibly very large number of BGP prefixes. This work, again, as I mentioned, is applicable to both BGP and anything else. Could be pseudowires, could be DPLS, could be anything else. Although in this draft, we focus only on BGP. One last thing is the benefit, or how do we gracefully handle the loss of number of levels of recursion. So remember this scenario, I'm not sure if it is realistic or not, but this is not the point here, that I had here 3 levels of recursion. Suppose this ASBR dies. So this is my forwarding chain. This is my original forwarding chain before the ASBR dies. When it died, I only need to change one path list only in the entire hierarchy. I did not need to change anything else. Just because something failed, I need to change one thing only. Could be few, again. As I said, it's not going to be 1, but it's not going to be 100,000. Maybe 20, 30, maybe 100, 200.
2 minutes.
2 minutes, yeah, I'm about to finish. It's pretty much, I think the next slide is the last one. Now, we said that there is a scenario where I do not have 3 levels of recursion, or 3 levels of hierarchy. I had this place where I collapsed one path list into 2. Now, when this link dies, now I need to go and change when this node dies, which means that ASBR is no longer reachable. Instead of, in the previous slide, I needed to change one path list only. Now I need to change 2 path lists. So the price that I paid is that I had to change a little bit extra, but I did not lose the entire benefit of BGP pick. Point here is that you can gracefully recover from the loss of your hierarchy of levels of ASIC. However, eventually, if you don't have enough hierarchy, you will end up losing completely BGP pick. This is my last slide, basically. So what did we do here? We just have a simple design that actually runs very efficiently, could run on a simple line card. It works for any recursion, whether it's BGP or anything else. It supports any number of hierarchy depth with graceful degradation in performance as you reduce the number of hierarchy levels. And I would request this document to be a working group document. Any questions?
I'm Tony P. Erickson. Yeah, so this is relevant for vendors. Interesting work, but what kind of track does it go on? Is it BCP?
Informational.
Is it informational?
Informational, probably. I mean, when I wrote the draft, I wrote it informational. Like BCP.
Because it I mean,
It could
BCP
be
is
BC.
dangerous.
Yeah, you're right.
Informational is okay. The world is more complicated than that, right? FRR plays in inter-chassis redundancy. People have all kind of interesting things that are on top of the whole thing. So it's not like you can take that and build, you know, world-class router. Okay, yeah.
Yeah, this is informational mostly. I mean, when I wrote the draft, it's informational.
So from my perspective, it would be informational. Every vendor here built very similar solution. I think it would be very useful for service providers, for people who try to understand how it works. And I would really like Ahmed to kind of enhance this work, explaining why do you need next hop redundancy in BGP, otherwise it doesn't work. Why do you need tunnels in PC protection? And it would be extremely useful. Tens of service providers have deployed this technology on different vendors, so from informational perspective, it is very needed work.
So it's basically to educate service provider to have a more qualified discussion with vendors. Yeah, okay, then yeah, it definitely serves a good purpose. Thanks.
Any other question? Okay, thank you very much.
Thank you, and I would really encourage you to enhance it. It's control plane, not why do or why not do particular things, add pass diverse and such.
Yeah, I actually discussed this a little bit, but I thought it's a little bit out of scope because BGP multipath is a bigger discussion. So I did not want to get into it within this document. Thank you very much.
Hello, this is Pushpashish from Juniper. I'm here to present the first version of this draft called Microloop Prevention Using Spring. So here's the agenda. We'll go through the problem statement and a little bit of solution, and then cover some facts about multiple events handling, partial deployment, and the protocol extensions, the need for it that we have proposed in this draft. So to start with the problem statement, we have taken an example network to show how microloops can form. But essentially, microloops are nothing but transient loops caused because of unsynchronized fib updates on different nodes. And and there are facts that certain topologies are more prone to microloops, especially the ring type of topologies. So in this example, if the link between the node 3 and 4 goes down, we can see there will be some microloops occurring. So here we see the new SPF paths, which is supposed to happen after the the IGP convergence. And in this, if you really see, there's not only a local microloop attached to the node 3, there's also some remote microloops between the node 2, 9, 1, and 6, right? So essentially, the purpose of this draft is solve microloop and using Spring, but the solution is based on RFC 5715 solution, which is called the near-end tunneling solution. And the basics of that is found this proposal is founded on the fact that the tunnel from any ingress or source router all the way to the nearest PLR is always unaffected by the link or node event, right? So based on this fact, we come up with the solution, and this is in the next few slides. I'm going to actually go through a series of events which this draft proposes. So the first step is for the solution to work, all the nodes should be configured with the single max convergence delay, and using that value, there are a couple of steps that the solution proposes. Again, the first step is when the link actually, so I'm taking an example of a link down case, but the draft essentially covers a number of other cases as well. So when the link goes down, you basically, again, the assumption is that the PLR, the nearest PLR, will have some form of backup using LFA. So in this case, say I'm just looking at node 3, which is supposed to be the nearest PLR for all the sources on the left hand side. So the first step is that when the link goes down, instead of converging the primary path, the nearest PLRs will actually keep using the backup path, right? And then each of next step is when this event goes to or flows all the way to the other source routers, they will see whether based on the new SPF whether the primary path is converging or not, changing or not. If it is changing, instead of changing to the new next hops, they will tunnel the traffic to the old the nearest PLR basically. Nearest PLR on the old SPF path. So that's what this orange tunnels look like, and this will keep like this for the next interval of time, which is equivalent to D. So after time D, each of these non-PLR nodes will start converging to the new SPF path, and this is something how it will look like. So as they converge to the new path, the tunnels are not used anymore, and in the final step, which is after 2 times the interval, you converge the nearest PLRs.
Ashish, I have a question.
Okay.
So you said micro loop, right? In the earlier one. Can you help me to understand, like, why did you choose that path if it is a looping? It's LFA path. If it is a loop-free alternate path, then why would it cause a micro loop?
Oh, hold on. Okay, so let me go back to that slide. I think you're referring to this slide, right? If you really see those green arrows and red arrows, so this micro loop is mostly happens post-convergence, not pre-convergence. If say if node 3 converges before node 2, there is a loop, right?
Probably.
So that's what I've actually highlighted there. So wherever you see the two-way arrow, those are like potential loops. Yes, Tony?
Tony P. Erickson. Just clarification. So how would you trigger the failover on the tunnel? You see a new LSA from 03, which you didn't compute yet, SPF. What triggers the failover?
What is the trigger for each event? So again, so the first step trigger is the local event on the PLRs, and the second part is basically when this IGP floods this event to the rest of the routers.
There's a new version of LSA that you didn't SPF yet. So 3 floods something to 6 didn't SPF yet, it falls over to the tunnel?
Yeah, so so its draft is basically the proposal is that you do the SPF, but you still don't update your path. So your SPF will still find out the new paths, but it will not download them into FIB. So instead, they will download us another path. I have a slide. I'll show you. Okay, let's go. Yeah, I think this is the slide you probably will answer. So if you really see before the event, which is before T0, they were all using a single, kind of a tunnel to the destination. Destination is again 005, and sRGB is 1000 to 2005, and index is like similar to what the node numbers are. So there are two kind of things I'm trying to show here. One is the node 1, where the next hop actually changes because of the SPF that you run. But instead of converging to the next hop, forwarding via 006, you still send it to 009 and 9 and 2. Actually, there's a typo there. There should not be 003, it's 002. So, but you actually are using, instead of one label, you're going to use two labels. So first label is to take you to the nearest PLR, which is 1003 here. And then the second one is basically the label from the 1000, basically 003 to the final destination, 005. Okay. So the other thing I wanted to show here is that the node 008, it doesn't find a change in next hop because of SPF after running SPF. So it doesn't do anything here. It just keeps on sending with the same thing. And the third row you see in this table is basically how the nearest PLR reacts to the event.
3 minutes, you've got 10 slides.
Can I take it later?
Yeah,
I
don't know if it's a quick one. AC Lindum, Cisco. I see how this works, but what happens when Dmax convergence timer times out? What's to keep you from having micro loops at a second order between those all the nodes that are tunneling to node 3?
I think this is what you're so when this converges, right? I think again, say even this converges, but the next router has not, then they will still again come back to the nearest PLR.
Right, but how long do you keep those? How long do you keep using that tunnel, and what happens at max when that expires? And all those other nodes, do they ever go back onto the routed path when?
Yeah, so that's the step I'm showing here. So they are finally going back to the new SPF paths. So the last step is where the nearest PLRs are going to actually converge to the new path. Okay, so so long I was actually describing the case of link down, but along with link down, we have a couple of other procedures for taking care of these kind of events as well. This is a slide on handling multiple events. We have added text in the draft for how to handle multiple events as well. And there are cases which we have called out that it will not be handled. For example, this multiple network events which are not part of the same SRLG, cannot be handled. And then we have some detailed discussions in the document as to how to find out the nearest PLRs, because there can be a varied amount of or varied order of receiving events from the network. Finally, a slide on partial deployments. Our draft basically proposes that all the nodes should be supporting this capability, and then only some ingress node or anything should be using this. And so for the same case, the nodes need to know whether other nodes in the network are supporting this capability or not. So there's some protocol extensions also proposed in the draft. And we have found out that in certain cases of partial deployment, where the ingresses supports this functionality, but the nearest PLR does not, can cause increased amount of loop. Finally, these are the protocol extensions that we have proposed in the draft, and probably this will go into, I'm not sure, this might go into the corresponding protocol working group as well. Yeah, so I'm done. This is the first version of the draft, and we will request members to actually come up with comments, suggestions to improve this draft. Okay.
So I've got a specific question to service provider. We've been trying to fight micro looping for quite some time. There have been many proposals, none of which was really deployed due to complexity. So would you really be willing to deploy something described here to prevent microlooping? Thank you.
Bruno Ducran, Orange. Yes, we need a solution for microloops. Otherwise, it kills the benefits of fast reroute, because you have protected your traffic in, say, 50 milliseconds. But then you have IGP convergence, and you may have microloops for 500 or 500 milliseconds or 2 seconds. So if you care for fast reroute, you should care for fast convergence. No, you should care for microloops avoidance.
We all agree we need somehow to prevent microlooping. The question is what cost. And again, I would really like to read you the draft and see whether you see this applicable and whether you would be willing to deploy something like that.
Okay. Think about it.
Hi, my name is Zanil Kumar. I'm from Huawei. And this is like, we want to have MRT in segment routing domain. So we found it very effective. So yeah, we found it very effective algorithm, MRT. I mean, I implemented MRT and I found it like really good. So it was not there for segment routing. So we thought of like extending it to segment routing. So let's see like why it makes sense and like forwarding mechanism and Spring, like how it is like when MRT was first done, like it was done for LDP domain. So those things, like there were two options provided, like how it fits into Spring and whether like there is a TILFA and like how better it can complement TILFA and what IGP support is needed and like conclusion. So because like when you see MRT was done for LDP scenario, like IGP extension is defined and the same extensions with added few extra thing we can support it for Spring. And then like since there is a topology label we can define for 3 topologies, so that is red, blue and rainbow, we can easily support MRT in Spring. And MRT is not competing TILFA, it complements. So having two good FRR algorithm for a Spring is not a bad thing, I feel. And changes are very minimal. And for Spring, like there are two options provided in LDP extension. That is like one label indicates both prefix and MTID. Other one is like a separate label for a MTID and a prefix label. So these two can be easily supported in Spring. So this would be the label stack. Like first option is like a red prefix label for a destination where you want to redirect the packet, and then followed by normal payload. Other one is like a top label is a topology segment, that is like, and then next is a prefix to the destination where you want to redirect the packet. So what would be the support needed? Like we just need to exchange the capability, that is like SR supports MRT, and then like when case of like default profile, we have a fixed MTIDs that is like red, blue, and rainbow that is like allotted by IANA. In case of non-default, we need to have a consensus like, okay, what MTID will be using, like what free MTID will be used across the domain for all three, and the same thing has to be advertised. And I feel like it's useful. Like there are cases where like both TLFA and MRT has advantages and disadvantages. So in case of MRT, like computation is very efficient. So when there is a device who can compute well, but the compute, like its computation power is low, and he has got a very good forwarding entry size. So that time I think MRT can be used, such as like in access or like aggregation area. So that's all. Any suggestions and comments?
So yeah, I'll plan to share those comments with you later on. But yeah, I've quite a few comments to make, but in general, it's good work.
Anything else?
Thank you.
Yeah. So I was planning to just share them offline as individual contributor.
Hello, everyone. My name is Yingzhen from Cisco. This is an update of the keychain YANG model. Okay, so when we were defining the OSPF and the ISS data model, we realized the requirement of a common keychain model. So the routing protocols can use it for authentication. The keychain model is defined as a list of keys. Each key has a key string, the send, accept, lifetime, and also the crypto algorithm related with the key. This data model has been presented before, so the overall structure stays the same. We didn't change it. So what's new this time? Last IETF, the major comments we got is the keychain model doesn't support any encryption for the key string. So we added a key encryption using the advanced encryption standard key wrap. So you can, this is defined as the keychain level. So you can enable and disable it. Once it's enabled, it applies to all the keys defined in the keychain. We also added a new crypto algorithm to the algorithm choice list. It's just a new case and it's defined. We also made it as a feature. So this is the overall keychain data structure. The bottom few ones in bold are the new items. We made changes this time. So the keychain model defines, provides a reusable authentication and encryption policy. It can be used by, it's already being used by OSPF and ISS, and it can be also used by other protocols and routing protocols. When we designed the model, we made it in a way so it can be easily used and augmented. And so far we think the model is mature and complete, and we'd like to request a working group adoption.
So on 3rd, the same draft is going to be presented in security area, and based on their comment, and hopefully they'll agree it's important. And I think in this area we all agree it's used everywhere and important. And when security area comments have been addressed, I believe we could proceed with working group adoption. Helen?
Yes, it's Thursday. So, any questions for this model?
Have a question?
So we added those 2 more things based on discussions with Brian Weiss. And the reason we added that one algorithm that nobody supports yet is it's the one that's recommended for TCP/AO. So that's why you might wonder why we added something nobody supports. But that's why we made, and so we made it a feature.
Dan Bogdanovic. I would recommend looking into removing the time, the time leaves out of the model, because it might be useful to define a separate model that would deal with, lifetime, because we are looking, you don't want to have different lifetime time ranges, supported, actually defined in different models. So maybe.
I mean, I have to see it before I see this reusable piece you've been talking about, whether it really is a good thing to have too many little pieces, because
it's open for discussion, but just something to think about.
Yeah, right. You recommend. Let's
Dan,
see, because
just to understand your suggestion, it was a generically reusable lifetime.
Yes, generically reusable, because we have it in access control list. There's in multiple different ways we're defining, like lifetime of something, and just defining it as a separate model that can be reused in different models
as a type. Yes.
Instead of
that's
defining
in
each model,
if it's a generic
lifetime.
type with different. I mean, that's okay, but I think I know what you mean. You mean you're going to have something, you're going to have it either it's a duration or if it's a start and end or something generic like that. Okay.
Yeah. So we'd like to take a look at what you mentioned and see whether we can reuse that.
Would be good if you could publish on the list your comment and explain where time model is going to be implemented by who and how. Thank you.
Okay, so this is a young data model for RIP extensions. It's augmenting the routing config model with small RIP attributes. So we know RIP is an entity that contains all the routes calculated by routing protocols. So for all router implementations, smaller or larger ones, they all support a RIP. The routing config model defines the basic building blocks for RIP, and it's expected to be augmented with small RIP attributes. So this is what's currently defined in the routing config model. So it defines a list of routes, but for each route, you can see here, the next hop options are very limited. Besides the specific next hop, so your next hop can only be either one outgoing interface or an IP address. So it doesn't support things like ECMP, which is a very common use case. For route attributes, it only defines the route preference here. So obviously, we need to augment this model with more stuff. As I mentioned, the routing config model doesn't support the ECMP, so we added multi-path option to the next hop choice list. It's defined as a list of path entries. And for each path, you need to define a unique combination of interface and IP address. So by this, we can support ECMP. And since routing config model only defined a route preference for each route, and so we are adding more route and path attributes, metric, tag, and repair path. Repair path is the loop-free alternate fast reroute repair path calculated by routing protocols. For each path, there is a repair path defined with the next hop of interface and IP address, and also metric and tag related with this repair path. Put everything together, this is the extensions, this is the RIB extensions tree that we are adding, we are augmenting to every path. So it consists of a metric, a tag, and a repair path. So the tree structure showed in this slide is augmenting to every next hop options. And for the multi-path next hop options, we can support not only ECMP, because we also have a metric related with each path. We can also support unequal cost multi-path. We also augmented the static route configuration with multiple next hop support. So it's also defined as a list with the list of next hop entries. The next hop is a combination of interface and address, and also preference and tag related with each path. The examples showing here, we are just using an IPv4 as an example. We did the same augmentation for IPv6. The only difference is the IP address is an IPv6. So in summary, we have defined more RIB attributes, and together with the routing config model, we defined a very generic model. It's common enough, and we believe hopefully all vendor implementations support all these attributes. And it also includes pretty much all the basic attributes required for a RIB model. And questions or comments?
Jeff, I was speaking as an I2RS chair. The work you're doing here is very interesting because two things. First one, we know the netmod config module was very simple. It needed this. The second thing is the I2RS RIB data model. One of the big things that it differs from the netmod config is more complicated next hop types. We are far enough along in the I2RS model that we have been requested to look at potentially refactoring against the routing config module to remove redundancy. This makes design sense. My request to you is, could you talk to the RIB data model authors within I2RS about this, simply because I think that it actually makes sense for our two groups to come to a common understanding of what the next hop should be, and potentially what may happen from I2RS is that our model largely disappears, and that would actually be a good thing. It means that we succeeded.
Dan Bogdanovic, there's actually one more model that has to be also taken into the relation. It's the device meta model. So there are also, that has to be then put together because we're introducing some construct that are neither present in the I2RS model, Lala's model, nor your model. So.
Sorry, I didn't get the model you mentioned.
There's a device model design team within the routing group, And we published a draft that how young models should be organized to represent a device. And within that model, how the routing configuration is done doesn't, correlate nicely what we have proposed. So because it impacts the I2RS RIB model and also partially yours. So that is something that AC will present, I believe, on Thursday.
Yeah.
Okay, yeah. The major thing is this model is a direct augmentation of the routing config model. So if your some implementation that's already support the routing config model, this one is very easy to do. Just add more, a few more common RIB attributes. Yeah.
Do you plan to present in net mode since the direct augmentation of? So one comment is without share. I think for ECMP cases and fast route would be great to also augment with weight, which is needed when you do non-equal CMP.
I have one more comment with regards to the RIB model. Yeah, that's a question because as Trill and PBB are using layer 2 routing, and you put in IPv4 address, and it seems like you made it very IP specific. I think this, the same augmentation could be just reused. The actual model could be reused for other layers. So making it, less IP layer 3 specific would be useful.
Yeah, so far this model mainly focuses on layer 3 only.
So please more discussion on the list and then specifically please Bob, whatever you just described.
Yeah, there's one other model. I don't know, is Rob in the room? He's not. There's also a local route model from OpenConfig that also has overlap with this, and it has static routes and aggregates in that. So I'd like to maybe get them all together.
Sounds like a great idea.
Yeah.
Sounds like we need to have a meeting about RIP. Okay, thank you.
So thank you everybody and see you Thursday. Sure, before we publish. Yeah. But you did seem surprised, right? Yeah. So, let's take one or two together. I'm done with it. Yeah. The marketing. Yeah, no, this is cool. I'm just. Yes, I there's people who probably for people. For the key, but not the security part. Or maybe